Okay, in order to find the inverse of the following log function, my first step is to switch x and y. So I have x is equal to log base 2 of y minus 1 plus 3. My second step is to then isolate for the logarithm for the new y value. So based on this information, I will subtract 3 on both sides. On the left-hand side, x minus 3 are not like terms, so hence I keep them separated with the operation of subtraction. So I have x minus 3 is equal to log base 2 of y minus 1. In order to get to y all by itself, I will then convert this to the exponential form. So I have 2 to the power of x minus 3 is equal to y minus 1. And again, my goal is to get y all by itself. I notice that I have y minus 1, so I will add 1 on both sides. Keep in mind that this 1 and the 2 are not like terms. 2 is an exponential term with the x minus 3 exponent, and 1 is just simply a constant. So I have 2 to the power of x minus 3 plus 1 is equal to y. So did I get y all by itself? Yes, I did. So my final step is to simply rewrite y to be the inverse notation. So I have y to the negative 1. But again, we don't say y to the negative 1. We say the inverse of y is equal to 2 to the power of x minus 3 plus 1. Let's go ahead and box that in. Keep in mind that you can prove this graphically on Desmos. If you were to graph this function right here and this function right here, your graph should be symmetrical across the y equals x axis. If it's symmetrical, if you see symmetry, then you did it correctly. Let's go ahead and move on to the second example. So we just showed how to do this for the inverse of a logarithm. What about the inverse of a natural log? Let's say that we have y equals natural log of x plus 3. Now, before we start, I want to remind you that if we do not have a base for the natural log ln, we know that it's known to be a base of e, the natural base e. From there, let's go ahead and find the inverse. My first step is to switch x and y. So I have x is equal to the natural log of y plus 3. I will then isolate for my logarithm. If you look right here for the logarithm or the natural log, you notice that it's all by itself. It's isolated. There's no addition, there's no subtraction, multiplication, or division occurring outside of the natural log. Hence, we then convert this to the exponential form. But keep in mind that this has a base of e. From there, we then convert it. This is going to go ahead and give us e to the power of x is equal to y plus 3. Keep in mind that your goal is to get y to be all by itself. So I notice that I have y plus 3. I will get rid of the plus 3 by subtracting on both sides. This will leave me with e to the power of x minus 3 is equal to y. Or essentially, y is equal to the power of x minus 3. I just simply rewrote it. So did I get y to be all by itself? Yes, I did. So my final step is to rewrite this to be the inverse notation. So I have the inverse of y is equal to e to the power of x minus 3. And if you were to graph this function as well as the original function, you will notice that there is symmetry across the line y equals x. And I believe I mentioned this right here earlier, but it should be for the graph of this one and the original right here. If you were to graph them, you would get symmetry across the line y equals x. Okay, So let's go ahead and jump into some further examples. We have find the inverse of the following log functions. For the first one, my first step is to rewrite f of x to be y. So I have y equals log base 3 of x plus 4. I will then switch x and y. So I have x is equal to log base 3 of y plus 4. I will then isolate for my logarithm. So looking at this logarithm, there's no addition or subtraction occurring outside of it, and there's no multiplication or division occurring in front of it. So from there, we will then convert this to the exponential form. I have 3 to the power of x is equal to y plus 4. Keep in mind that your goal is to get y to be all by itself. So looking at this, we will subtract 4 on both sides. This will now leave me with 3 to the power of x minus 4 is equal to y. Or essentially, y is equal to 3 to the power of x minus 4. So did I get y to be all by itself? Yes, I did. So my final step is to simply rewrite this to be the inverse of f of x. So we have the inverse of f of x is equal to 3 to the power of x minus 4. Let's go ahead and box that in. Keep in mind that you can identify and determine whether you did this correctly or not by just simply graphing the original function, the inverse function, and the y equals x. If you see symmetry across the line y equals x, then most likely you did it correctly. Let's go ahead and move on to the second example. For the second example, we have f of x equals 3 times log base 2 of x. My first step is to rewrite f of x to be y. So we have y equals 3 times log base 2 of x. My next step is to then switch x and y. So we have x equals 3 times log base 2 of y. From there, we will then get rid of any addition, subtraction, multiplication, or division outside of the logarithm. Essentially, we want to isolate for the logarithm. So from here, we notice that we have a 3 in front of our log expression. Keep in mind that if you ever have a number in front, it is known as multiplication. So we do the opposite to get rid of it. We divide both sides by 3. Then this will leave us with x over 3 is equal to log base 2 of y. So did I get y to be all by itself? Not yet, but I did get my logarithm to be all by itself, isolated. So I will then convert this to the exponential form. This will go ahead and leave me with 2 to the power of x over 3 is equal to y. Or essentially, y is equal to 2 to the power of x over 3. So from there, did I get y all by itself? Yes, I did. So my final step is to simply rewrite this to be the inverse of f of x. Let's go ahead and write that down. The inverse of f of x is equal to 2 to the power of x over 3. Let's go ahead and box that in. Keep in mind that you can verify whether or not you did this correctly by simply graphing the original function, f of x, and the inverse function, 2 to the power of x over 3. And if you see symmetry across the line y equals x, then most likely you did it correctly. Let's go ahead and jump into the third example. For the third example, again, don't jump ahead. You don't want to isolate just yet for the logarithm. You want to rewrite f of x to be y. So we have y equals 1/4 log of x. Now, keep in mind that if there's no base written down for a regular logarithm, then it is known to be a base of 10. This is referred to as a common logarithm. Keep in mind that you might potentially see this on the multiple choice, so you have to know what this refers to. Okay, now, before you do any isolation for the logarithm, we want to interchange x and y. So we have x is equal to 1 over 4 log of y. From there, we will then multiply both sides by 4 to get rid of any terms outside of the logarithm. From there, on the right-hand side, the 4's cancel out. And on the left-hand side, you're left with 4x is equal to 1 times the logarithm will remain the same, so log of y. So did I get my logarithm all by itself? Yes, I did. So my next step is to convert this to the exponential form. So this will leave me with 10 to the power of 4x is equal to y. Or essentially, y is equal to 10 to the power of 4x. So did I get y to be all by itself? Yes, I did. So my next step is to rewrite this to be the inverse notation. So we have the inverse of f of x is equal to 10 to the power of 4x. Let's go ahead and box that in. Keep in mind that you can verify that this is correct by just simply typing in the original function, the inverse function, and the y equals x into Desmos. And if you see that the graphs are symmetrical across y equals x, then most likely you did it correctly. Let's go ahead and move on to some natural logs, okay? So for the first one, we have f of x equals 2 times natural log of x minus 4. My first step is to rewrite f of x to be y. So we have y equals 2 times natural log of x minus 4. Now, before you switch the before you isolate for the natural log, you want to switch x and y, okay? So we have x is equal to 2 times the natural log of x minus 4. Keep in mind that the base of the natural log is e, okay? So before we do that, we want to go ahead and isolate for the logarithm, the natural log, by dividing both sides by 2. So on the left-hand side, we have x divided by 2. On the right-hand side, the 2's cancel out, and we're left with the natural log of x. That should be a y. Okay, let me just erase that real quick. So that should be a y. This should be a y. Okay, if you caught that, awesome. Good job for you. Okay, and we have y minus 4. Okay, now I will go ahead and convert this to the exponential form. So I have e to the power of x over 2 is equal to y minus 4. But again, your goal is to get y to be all by itself. I notice that I have a minus 4. So I will do the opposite of that, plus 4, plus 4. Now, keep in mind that 4 and e to the power of x over 2 are not like terms. Do not combine them. Keep them separated with the operation of addition, okay? So we have e to the power of x over 2 plus 4 is equal to y. Or essentially, we have y equals e to the power of x over 2 plus 4. Okay, so did I get y to be all by itself? Yes, I did. So my final step is to rewrite f of x to be the inverse of f of x. So we have the inverse of f of x is equal to e to the power of x over 2 plus 4. And let's go ahead and box that in. And that's going to be my final solution. Now, you can also verify that this is correctly done by just simply typing this original function into Desmos, the inverse function into Desmos, the y equals x, and if you see symmetry across the line, y equals x, then you did it correctly. If you do not see any symmetry, then most likely something went wrong. Okay, let's move on to our last question. F of x equals the negative natural log of x plus 6. My first step is to rewrite f of x to be y. So we have y equals negative natural log of x plus 6. My next step, before I do any division by -1 or any subtraction by 6, I need to switch x and y. So I have x is equal to negative natural log of y plus 6. I will then work with the subtraction first. Keep in mind, you always want to do addition and subtraction first when isolating for a specific variable. So we will subtract 6 on both sides. Keep in mind that 6 and x are not like terms. Keep them separated. X minus 6 is equal to negative natural log of y. The 6's cancel out on the right-hand side. Okay, and from there, keep in mind, we have a negative natural log. So what does that mean? That there's a negative 1 in front of our natural log. So in order to get rid of it, we will divide both sides by negative 1. And we will do the same idea on the left-hand side for both terms. Now, when you divide by a negative, you have to distribute because most likely this might be a multiple choice or perhaps it might be a free response. It's a good idea to distribute the negative symbol to both to both numerator terms, okay? So what does that mean? It will change the signs for them. So we now have negative x, and we have what? Instead of a negative 6, we have a plus 6, all divided by 1. But keep in mind that if we divide by 1, we do not need to write that down. It will not change it. For example, 7 divided by 1 is still 7, right? 8 divided by 1 is still 8. So the division by 1 is not going to change anything. We can just keep it out of the way. Is equal to the natural log of y. So did I get the natural log all by itself? Yes, I did. So my next step is to convert this to the exponential form. So I have e to the negative x plus 6 is equal to y. Or essentially, I have y equals e to the negative x plus 6. And I ask myself, did I get y to be all by itself? Yes, I did. So my final step is to simply rewrite the inverse of f of x is equal to e to the negative x plus 6. Let's go ahead and box that up. Now, again, you can check your solution by just simply typing in this first function, the original, as well as the inverse. And if you see